Hello, everyone. Thank you for joining this session. We're going to talk about how we do data processing at Spotify and a little bit about our journey to where we are right now and why we think portability matters. I'm Felipe Bragadas. I'm a data engineer at Spotify. I've been with the company for 5 years now, and I'm based in New York. Here with me, it's my colleague.
Hey, hi. Thanks for joining the talk. I'm Julian. I've been working for Spotify for the last 3 years almost, with Philip in a department called Data and Insights. So before we start the talk, I want to give you like a rough idea about how big Spotify is in terms of the data that we process. So in case you don't know it, Spotify is an audio streaming subscription service. I'm pretty sure most of you know it. We have about 140 million subscribers. So that is people that actually pay every month to use Spotify. About 300 million monthly active users. So what that means is that for any period of 30 days, you will have 300 million different people that use Spotify to listen to something at least once. 60 million songs, about 4 billion playlists, and we are available on 92 markets. So I think that should give you a rough idea about like how big we're talking with. Say we're doing data processing at Spotify. So a few words about why we do data processing. We have a bunch of use cases, so I'm sure that you can imagine that when an artist publishes their music on Spotify, we need to pay them. So of course, that's one of the use cases. We want to know who's listening to what, so that we can repay the artist. But like on a perhaps like a more fun side of thing, we have like a bunch of tools like Discover Weekly, which you might know if you use Spotify, which is a personalized playlist that we generate every week, where it's gonna pick songs for you that you don't know but you might like. We also have something called Release Radar, which are new songs that have just been released and you are likely to like. Daily mixes, kind of like the same thing. We're going to generate playlists for you every day, or a bunch of playlists based on what you've been listening to. And perhaps like a more interesting one, your year wraps. That one's actually in the end of the year, we collect and generate statistics about what you've been listening to. It sort of tells you like what kind of listener you are. And I think this one is super interesting because it's a massive job. It processes the entire year worth of data for all of our users. So you can imagine 300 million people use Spotify every month. We do computation over the entire data that we have for an entire year. And on a perhaps like a side of Spotify that you might not know unless you're an artist, we have something called Find Insights, which is just analytics basically for artists, where they can see what people are doing and when they're listening to their music and where are their fans and what they're doing. So a bunch of different use cases spawning across like different sides of Spotify to do like various tasks. In terms of the size of the company and the number of jobs we're running, we're talking about 900 people who at some point at Spotify either work every day with data processing or do a bit of data processing. And we're working here with different types of engineers. Data engineer, of course, writes a data pipeline, but also data scientist. And it's from time to time, backend engineer write a bit of data processing jobs. We have about 11,000 unique data pipelines currently deployed in production at Spotify, and that accounts for about 60,000 executions every day. We collect about 600 billion events every day. So that's events from our clients. So when you play a song, for example, that's trigger an event. And we do both batch and streaming pipelines. Right, so I'm going to let Philip give you a few words about what we use to do this.
Yeah, so for data processing at Spotify, we use Scio. Scio is a Scala API based on Apache Beam that lets you create batch and streaming pipelines that can run on any execution engine like Dataflow, Spark, Flink. Because it's based on Scala, we can actually leverage a lot of its features to allow users to make idiomatic, concise, and type-safe jobs without compromising their productivity. On the left side, we can actually see an example of a Scio job. And we can see, even if it is a naive word count, we can see that it's very concise and very easy to read. So because, as I mentioned, Scio is used to define all of our data processing jobs, it's a very fundamental piece in the Spotify's tech stack, and by extent, so it's Scala. And because we use Scala a lot, and because we like it a lot as well, we like to contribute back to the to the community. We are a member of the Scala Center Advisory Board, and we tend to open source most of our libraries under the GitHub Spotify org. You will find Scio there, and you can find a lot of other libraries, for example, Magnolify, that can help you convert between data types easily. You can find some ML-related libraries like Featuren for ML feature extraction, and many other libraries. Please check it out and let us know.
Right. So let's move on to the actual topic of this presentation. So the talk is called why portability. Why 1, 2, 3? Sorry, why portability matters. So to illustrate this, I want to give you a couple of examples that you might have encountered, or things that might have happened to you when you're an engineer. So first example, let's say that you are an engineer, a data engineer, and you work in a company, and the company is starting its data processing journey. So it just has like some data sitting somewhere, and it's like, okay, we actually need to process big data now, and we don't really have anything there yet. So if you end up in that situation, which I'm sure you have, basically you have many choices that you're going to have to make up front, right? So the first one, and the most obvious one, of course, is going to be which runtime are you going to use? Do you want to go with Hadoop? Do you want to go with Spark? Would you go with Flink? I'm sure you guys want to go with Flink, or maybe something else. Who knows? Once you've made that choice, you will have to decide how you're going to host that, right? Where are you going to install your cluster? Do you want to maintain your own servers? Do you want to have like an on-premise data center where you install your runtime? Do you want to deploy on the cloud? Do you want to do multi-cloud? Like maybe you want a bit more reliability, like say you want to go with AWS, but then you're like, okay, but what if something goes wrong with AWS? And maybe you want to go with a hybrid cloud, right? Where you have both a cloud install and an on-premise server. That could be like for cost reasons, security, yeah, whatever. Once you've made that choice, and assuming you go with the cloud solution, then you're going to have to choose a cloud provider, right? So you have many options. You can go with GCP, AWS, Azure, Databricks, and a lot more. And of course, the choice of the runtime will influence that, right? If you decide to go with Flink, then maybe you don't have that many options in terms of cloud provider. But then if you go with Spark, then maybe that's a bit easier, who knows? One thing that's absolutely sure, though, is that you don't want to be locked in, right? You want to have the freedom to change your cloud provider, because you might decide in some time that it's getting too expensive, or maybe they're not fast enough, or maybe they're not reliable enough, who knows? But anyway, you definitely don't want to get stuck with any of those choices, right? You don't want to get stuck with your cloud provider. You also don't really want to get stuck with the runtime, and we'll see why. But anyway, you want some flexibility. One of the things that you will take into consideration is where will be your company in 3 years or in 5 years, because you don't want to have to change everything in 2 months, right? So once you made your choices, you want to make sure that they still make sense 3 years from now or 5 years from now. And the reason for that is that because changing any of those points, the runtime, the way you deploy it, do you go with cloud or not cloud, the cloud provider, changing anything of that is going to be massively expensive. But okay, so you make the choices, and let's say they work. So you work for your company like a couple of years, the company grows, and now you have a company that is data oriented. Like you have pipelines and people working with pipelines for some time. Cool. So what happens after a while is that you end up with many, many pipelines, right? Because over the course of 2 years or 3 years, you're going to write more pipelines. That's just naturally going to happen, probably. You're probably going to have more teams writing pipelines or working with data pipelines. Because, of course, the company is going to be growing. Your use case for data processing will grow. You have more use case, so you write more pipelines, and you have more people working on them. And you still don't want to be too locked in with any particular choice that you made. Because if you do, the more you use data processing, the more pipelines you deploy, the more people use data processing pipelines, the more expensive it gets to change anything, and the harder it gets. So if you hear this out, then you might think, well, that's fine. When I'm starting my data processing journey, when I have to make those choices about the runtime and how I deploy my pipeline, all I have to do is to make a very informed choice and really stick to it, right? So you might think, okay, that's fine. I'm going to read about all my options for like a month, make sure I know all that I can know about the solution that I have, the options that I have. I'm going to make sure I have an idea about what the company is doing right now and where it's going to be in a couple of years. And when I made a choice, I'm going to just commit to that choice and stick with it, right? And of course, how hard can it be? Like, we're engineer, we're smart, we can do this. Well, the problem is it's not easy, right? Can you make the choice? By definition, when you start your data processing journey, you don't know anything. You're starting, right? So do you know how fast you're going to need to scale? How much data you will have in 1 year? Do you know that? Probably not. Do you know how fast the company will be growing in the next months or years? Again, probably not. Do you know if you're going to have to handle sensitive data at some point? Because for legal reason, then the cloud might not be an option anymore because you need stuff to be stored in your country, for example. And that, again, you don't really know. It's going to come up with business. Do you know what your budget is? Probably. Do you know what it will be in 2 years? Maybe not again. Do you know if you need to support Python? Because if you go with Flink, well, that might not work. And again, you don't really know. It might come up with data scientists joining the company in a couple of years, and then going to say, I want to write Python because I'm doing audio processing, or I'm going to do Python because I'm doing machine learning. And do you know how the cloud provider will work with their solutions? Like, maybe they will decide that they want to deprecate something at some point, and again, you don't really know if that's going to happen. So there's a lot of things that are moving under your feet, and you really have no idea about what's going to happen in the next few months or years. So you can't really make a really informed decision that it's going to work for the next 5 years. That's just not going to happen. And this is, in our opinion, the reason why portability matters. You don't want to be stuck with a particular runtime. You want to be, as much as you can, independent from the actual runtime. Okay, so you might think now, well, okay, that's cool, that's all fine, but that guy is bullshitting me. It's never going to happen. I can make an informed choice, that's going to work. So I'm going to give you a bit of an example about what can happen for a company by talking about the history of data processing at Spotify. So this is one of the oldest picture that I could find from someone working with data at Spotify. It's actually from 2009. So Spotify was launched in 2008. So it's like 1 year after Spotify was created. And you see this very happy engineer on the right side sitting next to what was at the time the Hadoop cluster, which had an incident. And the Hadoop cluster is just those 15 machines sitting on the floor somewhere. So that was 2009. Okay, so that was kind of like the infancy of data processing at Spotify. Now, if you fast forward a few years, we're now in 2015, Spotify has 68 million monthly active users. It has an Hadoop cluster that has 1,000 nodes. They're using Hadoop, Hive, Crunch, Scalding, Luigi, a bunch of other tools to do data processing, and it generates about 20 terabytes of raw data every day. And this is the point where people at Spotify started to think that maybe they had a problem because the resources needed to process the jobs, the Hadoop job, had more than tripled over the course of 1 year. So when I say a year, like 2015, I'm actually talking like January or February. So this is like the beginning of 2015. So people were growing conscious that they had a problem. In 2016, Spotify had 96 million monthly active users. Data on the Hadoop cluster had grown from 30 petabytes to almost 70 petabytes in just a year. It was adding 100 terabytes of data every day, and the Hadoop cluster was now 2,000 nodes, which I think at the time was the biggest in Europe. And so in February, 2016, something called the doomsday clock was introduced. And so the idea behind the doomsday clock is that it was an experiment to try to guess at what point in the future the Hadoop cluster would run out of space. And so in February of that year, people started to think, well, okay, we have maybe 5 more months before we ran out of space completely on the Hadoop cluster. So that would actually mean like basically Spotify doesn't work anymore. So huge problem. And to add on top of that, you could think like, okay, I'm just going to add more servers to the cluster. I'm going to be fine. But actually, the data center was running out of physical space. So just doubling the size of the cluster was not exactly an option. Okay, so what happened the year after that? Spotify had 132 million monthly active users. The cluster had 500 more nodes, so 2,500 nodes, still the biggest in Europe at the time. More than 100 petabytes of capacity, more than 100 terabytes of memory on the cluster. And we were running about 20K jobs a day from 2,000 workflow, and 100 teams were actually writing jobs. And in terms of the technical solution that were used to run the job, it was just growing and growing. So Hadoop, Hive, Crunch, Scalding, Luigi, and No Spark and Storm, and a bunch of others. So in 2017, Spotify actually started to migrate to a different solution and actually started to migrate to the cloud. And migrating to the cloud actually was a work that finished 1 year later in 2018. At the point, Spotify was roughly at 160 million monthly active users. And in June, the Hadoop cluster was completely shut off. You can see one of my colleagues on the right side who's literally dismounting the cluster with a saw. So at that point, most of the jobs were actually ported and running on Scio. One thing I want to stress about that story is that the migration itself took 1 year, but the work of preparing the migration actually started well before that, and actually just preparing for that migration took 2 years. So moving from an on-premise Hadoop cluster to the cloud took Spotify 3 years, and that's a massive amount of time. And it was a pretty big effort. So one of the questions you might want to know now is like, why did you do this in the first place? Why would you want to impose that huge work to yourself? Why not just opening another data center somewhere? Well, the reason is like Spotify is not an infrastructure company. We are an audio processing company. So we don't want to spend most of our engineering time working on scaling up the cluster. That doesn't really make sense. So what was the strategy to achieve that? Like, how do you migrate this massive amount of data from your on-premise cluster to the cloud? Can you stop everything and just like copy the data to the cloud and just start from there? Well, it turned out that copying the data, just like moving the data literally from our servers to the cloud, would have taken more than 2 months, assuming a pretty fast connection. So not really an option. You can't really stop Spotify for 2 months, obviously. So Spotify went with running the jobs and on the cloud, and at the same time on-premise, and migrating gradually and copying the data along the way. So we had about 80,000 jobs just copying the data every day at some point. So the new jobs were written on the cloud, obviously, and the existing jobs were forklifted to the cloud. Right, so where are we today? We have 300 million active users, 11,000 pipelines, 60,000 execution day, 600 billion events generated by our clients every day. So we are much, much, much bigger now. So it did work out. But anyway, Philip, do you want to take it from there?
Yeah, this was an impressive journey that we had, and I guess we are a little bit lucky to have been part of it. It was a great experience, full of interesting challenges. But to be honest, it was painful. There was a lot of teams involved, like 100+ teams. There was a lot of fixing and a lot of re-engineering of our underlying infrastructure, so we could keep the boat floating, so we could keep our engineers focused on the product itself, because that's what matters. And along the way, while we were migrating, we were identifying a few things that could help us in the future when we need to face this again. Some of these things were already mentioned. We want to be vendor neutral, which means that we want our infrastructure to be based on standards, because it's more likely to be supported by all major cloud vendors, and it will most likely be well supported on on-premise situations. We want also our data processing jobs to run on different execution engines with little or no code change at all. This is also very useful in a non-migration context, because you're not really constrained to a specific set of properties and features provided by your current solution. So since some time has passed since our journey, like we finished in 2008, we're in 2020, we decided to run an experiment to see where we are right now. And we decided to take our data processing framework, Scio, and explore a new runtime. Spark was used in the past, but now we want to explore Flink. And why Flink? Because it has very interesting features. The upcoming roadmap looks very interesting with really good and promising features, and it has a very vibrant community. For this experiment, we just took an example from our Scio repo, and this was the job that we took from the example. As you can see, it doesn't really matter what it does. We can easily see that it reads from BigQuery, writes to BigQuery, and does some migration in between. And we started by using this job, and we started by running it on Dataflow. This would be the normal job you would see for this specific job, but I want you to notice how we actually ran the job. We started the job simply by running it from the command line, and note the red line there, the flag runner that specifies the runner to use. So in this case, we just set it to Dataflow runner. So the next step was to actually run it on Flink, and if you were guessing, that flag just was set to Flink runner. There's one additional flag that actually that tells where the cluster lives, and this would be the job graph that you would see for this specific job. This is a very familiar dashboard for all of you, I'm assuming. So we were able to, with no code change, run the two jobs, and so we kind of achieved the portable runtime point. But for this particular job, we actually needed to deploy Flink. And deploying Flink, to deploy Flink, we went with Kubernetes. There are a lot of talks that go a little bit more in depth about Kubernetes. Here, I'm just gonna throw some details about it. Kubernetes is the system, the de facto standard for container orchestration these days. It's a part of the Cloud Native Computing Foundation, which means that it's a very well supported project. It's vendor neutral, which means that all major cloud vendors will support Kubernetes, and most of them have their own managed products around Kubernetes. And it has a growing ecosystem. And Kubernetes has also allied to the growing ecosystem, it has a very large feature set. And one of the things is that allows you to extend the Kubernetes API in a way that makes use of custom resource definitions to actually allow you to create, manage, and deploy complex containerized applications. And in this case, we just these piece of softwares are called operators, and Flink operator is what allows us to easily deploy Flink clusters on Kubernetes. There are two flavors out there right now. One is provided by Google Cloud Platform. The other one is by our friends at Lyft. And both of them actually provide kind of the same feature set. If you deploy Flink on Kubernetes and you don't use Flink operators, you should definitely check it out because it makes your life a lot easier. So this kind of works, right? I mean, we are portable and we are vendor neutral. But in this case, we just used a kind of an Hello World job with, a small amount of data. And as we know, production jobs can actually have a completely different set of requirements. The amount of data that they handle, it's orders of magnitude higher. So immediately we found ourselves with a question: does it really work at our scale? I mean, as Julian talked about previously, we handle petabytes of data. We have jobs that process hundreds of terabytes a day. Can we actually have this setup work? So we actually went on a new experiment where we actually took a look at our production jobs. We actually picked a few that have a different set of requirements, like if they are CPU, memory, or shuffle intensive. In this experiment, we also wanted to make sure we use the same hardware, which means like we use the same instance types, the same persistent disk type and size, and we want to keep the no code change policy. We want to just take the job that is running right now in production and run it on Flink. And we want also to evaluate the user developer experience to see how it compares to our current solution. So the first job we actually took is our anonymization job. This is a job that is responsible for the encryption of sensitive data on events. It can handle 100 types of events. And in this case, for this particular experiment, we just took one event type that has like 500 gigs per partition and around like 1 billion events per partition. This job is a batch job. It reads from GCS and writes to BigQuery and GCS. And as it does encryption, it's very CPU intensive. And because we want to keep it as fast as we can, we want to avoid shuffling. On the left side, we can see some details about the stack we used, the versions of the frameworks we used, and the number of workers. And for this particular run, we actually used Flink 1.9. We took a second job in this experiment, and this job just basically imports metrics from GCS to BigQuery. And the particular thing about this job is it handles more than 114 terabytes per partition. And it's very shuffle intensive. As you can see, it uses like 400 workers per cluster. It handles a huge amount of data. And for this particular run, we used 1.10. So we managed to run these jobs successfully, and the overall experience, to be honest, was very, very good. But we were faced with some issues. We faced some dependency conflicts, especially with Cryo when it comes to serialization. We sometimes had a hard time to understand why things go wrong. Specifically, for example, why task managers were getting killed. Like the exceptions were not, the root cause for some of the exceptions was not very, very clear. And most of all, we realized that for our types of users, Julian was mentioning that we have backend engineers, data scientists producing and running data pipelines. It would require them to actually understand a little bit more of the underlying runtime. This is because they would need to actually understand how Flink memory management works, how to adjust the ratios, how to adjust the timeouts, and to be fair, the way it's done right now, from 1.9 to 1.10, there was a big improvement when it comes to memory management, and I think that it will continue to improve. But yeah, it's something to keep in mind. And also, we feel like the job graph, as you saw in the one of the slides before, the job graph right now, it's a bit overwhelming. It's very expanded compared to the Dataflow one, and for these types of users, it can be hard to actually grasp what the job is doing. But yeah, minor issues. Experience was good, and yeah, in a nutshell, these are the results that we got. We can see the thing that stands out right now is that the Flink execution takes a little bit more time than the Dataflow one. On the job one, it's 30% more, and on job two, which is the more shuffle intensive job, it takes 60% more. But overall, they all faced kind of the same issues. We saw degradation on combined operations compared to the Dataflow runner. But the other ones were just as fast. So we're kind of happy with these results. Julian, do you want to?
Sure. So, of course, now you might be thinking, well, that's a bit underwhelming. It was very slow. Why would you even look into this? Clearly not worth it. Well, yeah, but we did achieve the complete independence from the runtime, right? So we could take our job, not change anything in the code, and run them on Flink instead of Dataflow. The other thing that it actually scales. So we did try to add more nodes, our bigger cluster, our bigger machines, and see how it was performing. And we did see that if you add twice as many machines in your cluster, then the job goes twice as fast. That's pretty reassuring for bigger jobs. And what we did see too is that even without really looking for or profiling the code, we could actually see that it was possible to improve the runtime because you can work on Beam and improve the way that it translates the job to Flink. But anyway, so that was quite interesting. One of the things too you want to think about is that if you are in the situation where you have thousands of jobs running in production and you decide to change the runtime, it's a lot easier to actually improve the runtime or improve Scio or Beam than to rewrite all those jobs so that you can run them on a different runtime. And perhaps one of the more interesting insights that we had from this experiment was that being slower doesn't necessarily mean that it's going to be more expensive to run. That was quite surprising, and maybe you're surprised now to hear that. But actually, being independent from your runtime means that you have more option of runtime. So you can decide to run it on a completely different platform or using different products that your cloud provider is offering. And that means that you could actually achieve price parity or cost parity, or even be a bit cheaper, even though the runtime itself is slower. So I think that's a huge interesting insight that we gained there. Anyway, so a few words to end the talk. So how do we bridge the gap? Is it possible to actually make all that slower so that Flink on Scio could be, or Scio on Flink could be just as fast as just using Dataflow? Yeah, actually you could. What you have to do is benchmark and improve the Beam Flink runner. The Flink runner is actually just a few hundred lines of code, so that's totally doable. You can improve on that, and actually what needs to happen is benchmark and the scale of Spotify and providing a scale of the job that we see at Spotify. We need to benchmark Scio because we did realize that in some area, Scio was a bit not agnostic of the runtime. Like it was actually assuming some properties of the runtime that are not necessarily true. But that's it. Like that's what you have to do. And once you have that, you can have like something that's pretty close to be just as fast on any runtime. Anyway, I think that's all we have. So now is the time for questions if we have some. Here's a few links. You can check out Scio on GitHub. You can check out our Twitter account, and also on Slack we have a channel for open source questions about Scio. And of course, check out Spotify jobs. Maybe you will find something cool you want to work on. So that's all I have. Thanks for attending.